record button. And so again, with the organometallics, right? We talked about the different types. We talked about the Gilman, the Grignard, the different types of Gilman reagents, different types of Grignard reagents. And then one of the things that we talked about initially was what to use the organometallics for, right? And one of those things that we discussed was to use it for what we call coupling reactions. Right? And those were basically like substitution type reactions. I'm putting type because they're not all necessarily direct substitution.
We can use elimination sometimes. Is that what was said in the video?
Well, you have elimination if you do an addition to an ester, you will get elimination.
Oh, okay.
But for these coupling reactions, they're all basically like substitution type reactions.
Mm-hmm.
All right. So the way that I always like to, if you watch the video, the way that I always like to put this in context is to do CM plus RX, right? Well, CM is my organometallic, and then RX is the substrate that I'm reacting with, where X is some type of leaving group. Right? So in the case of coupling reactions, you're looking for X being like a halogen or some other type of good leaving group, like a triflate or a tosylate or something like that. And we're going to learn about what a triflate and tosylate is later on, but so don't panic about that. But the key to the reaction is that you're making a new bond between C and R, right? I really don't care about what happens to M and X because that's just going to get tossed anyway at the end of the reaction. But the goal is to make a bond, excuse me, make a bond between C and R, and then make a new carbon-carbon covalent bond. Right, that's the overall goal of the reaction. Right, so a new carbon-carbon covalent bond, that's facilitated by the organometallic reacting with some type of alkyl or vinyl or aryl halide. All right, so keep that in mind. The overall goal is to make a new carbon-carbon bond. All right. So let's look at this first example. And the best way to approach these problems is to first identify CM, right, where M is your metal and C is the carbon bound to it, and then identify RX. So on over here, this is a Grignard. And so we know that the Grignard is an organometallic, right? So CM is going to be this carbon right here, which is bound to magnesium. All right, so that's CM. Are you following?
Yes.
And then RX is going to be, if I find my leaving group, which in this case is iodine, right? That's RX. So these two carbons are what I'm trying to put together. Now the mechanism for these reactions kind of varies depending on what type of organometallic you're using. So I'm not really going to get into the arrow pushing part of it. I'm more concerned with what happens as a result of these two reacting together. And if you notice, everything is done in ether, which we've already discussed, as an aprotic solvent, and then at low temperature, so minus 78 degrees, right? So in the product, let me just draw this here, and then we'll discuss what happened, right? So here's this doesn't change, doesn't get touched. Right, here's the carbon that's in the ring. And sometimes it may help to keep that dot where carbon is, right? So you can see what's happening. Because one of the things that people normally do is they'll do this, not that, this, right? And that's not right, because what I've done is I've lost a carbon. Do you see how this alkene
You got connected to the
is
C.
connected to the carbon right outside of it? You follow me? So I can't just do away with that carbon, right? So in the product, instead of it looking like that, it's actually going to look like this, right? And I'm going to draw this out, even though the geometry might not match perfectly, but right. So here's the C from CM, and here's the R from RX. That's what you're trying to put together. Right. Any questions about that?
Wait. You changed it, right? Like it's not the exact. The
You mean
exact.
the way it's turned?
Yeah, is it turned?
Yeah. Yeah. It's not. It's still the same. It's still this same alkene right here. Right. That doesn't change.
Oh, I see. Okay.
All right. Let's go down to the bottom example because that's another Grignard. Right. So let's find CM. Which one do you think it is?
The one next to the.
Right.
It's the Grignard, right? So
Oh wait, no, the greener is my bad. MG. So right there.
so this is CM, and then this is RX. Is that right?
Mm-hmm.
So what two carbons are we trying to put together?
C and R.
Right. So I'm going to put a dot here and a dot here, right? Let me take that R out of the way. Right, and that's RX.
Okay, I'm still kind of confused as to how you're able to identify which one is CM and RX.
So the M is representative of the metal, right? And so all of these reactions are organometallic reactions. So I'm always looking for that metal carbon bond. That's how I know where CM is. Right, because that's the the main topic is organometallics. And then we talked about how to make them, and now we're talking about how to use them.
Okay, so then RX will be that carbon and that chlorine?
Yes, because X is the leaving group, right? And normally it's a halogen, but it's not always a halogen. For our class, it's going to be a halogen.
Is MG is the metal, right?
Mm-hmm.
Again.
Mm-hmm.
Mm-hmm.
All right. So in the product, right? That doesn't change. That's the carbon that where chlorine was. Is that right?
Mm-hmm.
And then I'm going to connect that to the carbon here. Like so.
Wait, Dr. So it doesn't matter if C C and M are first?
You mean what
Oh,
side it's on?
yeah, like,
No,
because I
no, that's all semantics. I moved it on purpose.
Mm-hmm.
Yeah, I moved it on purpose because I don't want you to get trapped into thinking that CM is always going to be on the left, RX is always going to be on the right. It doesn't matter.
Okay.
The only
As
thing
long
that, go ahead.
No, I just want to make sure. So it doesn't matter which side it's on, as
Mm-mm.
long as we're putting the C with the R.
That's all that matters.
Okay. You put C with the, okay.
Right? Because again, the overall goal is to make a new carbon bond in the product, right? And that's what we did right here.
Will we add the bromine magnesium with the chlorine?
Yeah.
Or no?
Yeah. But again, right, this part is inconsequential. It doesn't matter. Because you end up, anytime you do a reaction like this, you always have a step that's called a workup step, where you quench it, might add some acid or add water or some other type of quenching agent, and then you're going to separate out the organic from the aqueous, right? So that metal salt is always going to end up in your water layer, so it's not going to matter.
Okay.
All right, we're good for that. With that,
Yes.
Yes.
all right, let's go back up up top. Let's do this reaction right here. It's not a coupling, but I have copper iodine and I have 2 equivalents or 2 moles of this alkyl lithium. What am I doing there?
So, ooh.
Am I making a Gilman reagent? Is that how I make it?
Asking, is that how we're making it?
That's what I'm asking. Isn't that how we make the Gilman reagent?
Yeah. Yes, with
2
C.
equivalents of alkyl lithium plus copper iodine, right? So what did I get from that?
Hold on, let me look at it. R.
I'm going to get LII. Is that right? That's just a side product. And then I'm going to get
copper with
Copper lithium.
copper lithium, good. And then 2 of these pieces attached, right? At this carbon right here. So I'm going to draw that carbon, and that's connected to Is that okay?
There's 2 of them?
See the carbon right here? I just didn't draw out the CH3s.
Oh.
So when we're solving the problem, like on our homework, we don't have to draw the CH3. We could just do the carbon.
The methyl groups are always understood because they're at the end of a line.
So Dr. Russell,
Mm-hmm.
this isn't like the last example I know we did on Monday where there was like two of them where we had to add 2. So this is the same thing?
Yes.
So how would we know to add? Oh, it's right there. Never mind. There it is. Didn't see the 2.
You're talking about the stoichiometric coefficient?
Yeah. Okay. I didn't see that 2 right there when you zoomed in.
Yeah.
So, like, why did you draw it like that for the copper and lithium?
What do you mean?
Like how you have the, I don't know, the bonds. Drawing them like that chain you had last time.
Yeah, because that what I did was attach these two groups right here. Right, I attached two of them. Let me erase all this other stuff. Can you see how this group right here, how this carbon right here is what's attached to lithium?
Yeah.
So that's the carbon that's going to end up attached to copper, which is why I drew it like that over here. Can you see that up here?
Yes.
I'll put the CH3s in, that might help. Right, so it's not this carbon. Right, it's not this carbon that's attached to lithium, it's this one. All right, you see it now?
Yeah.
Okay. All right, let's do the next example. Now you have a Gilman. And you have this alkyl halide. Right, so where is Cm in the Gilman reagent? Remember, M is always for the representative of the metal.
Is it
The
the one to the left?
carbon I.
Yeah, so it's the carbon copper bond, isn't it?
Mm-hmm.
And this would be C, and that would be M. And then over here, that's
Rx.
that's X, and that's R. So it's this carbon right here. Is that right?
Mm-hmm.
And this carbon right here. Now notice for this, in this particular case, I have a parentheses and a subscript, and that's the same thing. That means there's two of those groups attached to copper.
Okay.
Right? So the thing about the Gilman that we didn't get a chance to talk about, but we'll talk about it now, is that when it does react as an organometallic, it only transfers one group, even though it has two groups attached to it. That's one of the drawbacks of using it, is you end up wasting one of your groups.
Even when we have that two subscript, we're just taking one.
Only one of those is going to transfer to Rx.
Is that only with
The
a
Gilman.
Gilman? Okay.
All right, so let's look at the product, and then we'll discuss it. I'm trying to keep all this stuff so I don't delete it. So I'm gonna do this. So that's that. That's my carbon where X was. All right, and I'm gonna connect that to here. Let me see how many carbons in that chain. 1, 2, 3 carbons. So
That's for the C.
Right, so this was R, this was C, and this was R, right? And this is the new bond between C and R.
Wait, could you zoom out again, please?
It says zoom out.
Yes, so I can see the. Oh, okay. I see.
You see it now?
Yeah, it just took me a minute.
Yeah, so so the Gilman is only going to transfer one group. So the other part of that is going to be this, right? So you have Cu with one of those groups attached to it, and then let's see. plus lithium iodide. All of these are side products from that reaction. So the copper gives up one of the alkyl groups and one stays, and then the lithium and the iodine from here end up together in the product. So that's where the lithium iodide comes from.
Why does the copper take one of those groups?
It had to give one up, right? Because we're doing a coupling.
Mm-hmm.
So it gave up one, and then it kept one. Because the carbon, if you look at the carbon where it went, you do see this part, right? Where this is where the group went to.
Yes.
But that carbon that it attacked, which is this one right here, I mean, it can only take that one group anyway.
Okay, so the other group has to go.
It just stays with copper. And again, once you get to this phase, all of this is crap. The copper and the lithium iodide, all that stuff goes in the trash.
Gotcha. Yeah, I gotta just train my brain that it doesn't have to be like CR. It could be like the RC. It's kind of throwing me off.
So if we're making the Gilman reagent, it transfer both carbons if there's two?
Yes.
Okay.
So it's when you make it with two groups attached to it. But when you use it in a coupling, only one of those groups gets transferred.
Okay.
All right. Any other questions about this part right here?
Yeah.
All right. So let's go down. Let me see what examples we got down here. I think I got a lot of greens. I got a lot of carbonyl additions. Well, let's talk about the carbonyl additions first, and then we'll look at some other examples. Right? Do you have any questions about the coupling part? Any other questions?
No, I don't think so.
Okay, I'm a little confused. Okay, so for the Gilman, you said you add both carbons, but you kind of did that in every example. So how would I be able to, besides not having two products?
Can you repeat the first part?
You said in the Gilman reactions that you'll add both carbons, but you kind of
So in the Gilman synthesis, when I'm making the Gilman reagent, I'm adding two carbons to copper. But when I actually use it in a reaction to do a coupling, even though it has two groups attached to it, you see right here how it has a subscript 2. Even though it has two groups attached to it, I'm only going to use one of those groups to do the coupling. So making it is one thing, and then applying it is something different. Did that answer your question?
Yeah, kind of.
Yeah, so when you use the Gilman, even though it has two organo groups attached to the metal, only one of them is going to be transferred to your substrate, your alkyl halide. All right. All right, so let's go down to here. All right. So we talked about the carbonyl additions. We didn't go into detail about how they happen, but we did talk about them in the sense that you can get an alcohol if you react to aldehyde or a ketone with a granular, or you can get a ketone from an ester. There's another reaction that you can do with the ester if you add in a second equivalent, but we'll talk about that in a minute. So up top, you see the basic format for these reactions, right? They happen in 2 steps. First, you add the granular, and then in the second step, you quench it, right? You can't add the H plus until after you add the granular. Somebody tell me why.
Because they'll react with each other.
Yeah, they'll react with each other, and your granular will just die, right? So you can't have the H plus at the same time as the granular. So that's why you have to do it in 2 steps. So sometimes you'll see it written like this, where you have in step 1, you add the granular, and then in step 2, you add the H plus. But the outcome is an alcohol like you see here, right? And if it's for aldehyde, you're gonna get a secondary alcohol. I'm gonna abbreviate alcohol. And then for a ketone, you'll get a tertiary alcohol. All right. So let's look at the mechanism, how it works, and then we're gonna look at some examples. Right. So the first step is, remember for the granular for any organometallic, the carbon is usually nucleophilic, right? Because we said that was a dipole here. That's the wrong way. Sorry. There's a dipole there. Carbon is partially negative, and magnesium is partially positive, right? And so that's why when you see the arrows coming from the granular towards the electrophile that it's attacking, right? The arrows is always going from the granular towards the electrophile. And if you notice here, I have the arrow here from the bond, right? Because that's where your electrons are coming from, right? And it's the carbon here that's going to end up attacking the carbonyl. All right, so when that's first you have that attack here, and then when you do that, you have to break the CO pi bond.
Okay.
Right, and so then that's how you end up with this intermediate.
Hey, can you explain what exactly intermediate is? Because I kind of understood it from the video, but I just want to make sure.
So anytime you have an intermediate, it's just basically, it's a species that is somewhere on the reaction profile between the start materials and the products, but it's not a transition state. Transition state is like a high energy species where bonds are made and broken, but then you can't isolate it. But the intermediate, you can actually isolate. Right, so an intermediate is any species that's on the path from start material to product that you can actually isolate. Because that's not the product, right?
Mm-hmm.
Right. So it's if it's not the product and it's not the start material, it's either intermediate or transition state.
Okay.
All right. And so now you see here, you see where the ring here with this carbon that attacked, right? And this is the carbonyl carbon. And then the oxygen, once you break that pi bond, let me put some electrons over here. Right, oxygen becomes negative, and that's where magnesium goes. Right, so they make a salt. And then when you protonate that with your acid, whatever acid you use, let me see if I can do this right quick. So that's negative, that's gonna attack H plus. Right, and that's where the OH group comes from over here.
And that's the product.
Mm-hmm. And remember, if you start out with an aldehyde, which we did right here, you're going to end up with a secondary alcohol.
Is it because we had a Grignard and an aldehyde?
Mm-hmm.
That's exactly.
Yeah. So a Grignard, there was a mnemonic I gave you, like Grignard plus an aldehyde or a ketone.
Here's your alcohol. Mm-hmm. And then did the magnesium bromide just it's just kind of floating around because of the because of the acid?
Yes. So it'll be plus whatever this is, because this is always going to be H something. Mm-hmm. It's never just H plus. I think we talked about that Wednesday. So it's going to be whatever that conjugate base is, and that's gonna make a salt with magnesium.
Do we always have to write it if there's an acid? I noticed like sometimes you don't. But.
Well, I would if I were you, because it's good practice. Right. Mm-hmm. I just leave it out because I'm old. I've been doing it for a long time.
I got you.
But yeah, for practice, I would definitely write it out.
And what's the X again? Is it the?
It's the conjugate base. So let's say if I used HCl for my acid, right? The X would be the chlorine.
Okay, right, gotcha.
Because once the acid gives up H plus, whatever is left, it's going to find magnesium and make a salt. Mm-hmm.
Got it.
All right. So let's go to here. We're going to do the aldehyde, the aldehyde, the ketone first, and then we'll come back and talk about the ester. And then we'll do the retrosynthesis tomorrow. I'm sorry, Friday, how to work backwards. All right. So here's my carbonyl. And here's the carbon that I'm going to be attacking. And then here is the carbon that's going to attack it. All right, so I want to get to the intermediate. I want to show the intermediate, and then we'll show the product. And notice it's in 2 steps. So first I'm going to add the Grignard, and then in the second step, I'm going to add H3O. All right. So I'm going to change the color on that, the part I added in. So this is the carbon that I'm adding. Right here. Mm-hmm. And then I have my oxygen is negatively charged because I broke the pi bond, right? So let me put the arrow in. I'm going from here to here. And then I'm going to break the CO pi bond. So now that oxygen is negative, and then magnesium iodine is here, just hanging out. Okay. Magnesium is positive.
This is the intermediate, right? We haven't got to the product.
right, and then I'm going to go, so that's my intermediate, and then I'm going to add H plus to that. But in this case, let's make up an acid because I don't want y'all to be, let's just use HCl. Because H3O plus can be, that's a generic, that can be any acid.
Oh, so it doesn't have to be H3O?
Like that can be any acid. I just need the H. I don't care about the rest of it. So this is going to attack here, break the HCl bond, and so now,
So we're just gonna have everything look the same, but have the H with the OH group. But then obviously the chlorine will be floating with the magnesium iodide.
Yep. So now this is OH, this is CH3, and then plus Mg, and I'm gonna put the chlorine. I'm gonna make that red, Cl.
This doesn't seem too bad. I just need to practice it.
It's not bad. It's just remembering what's what.
Yeah. Would it be okay, like, if we, with the homework we had to turn in, we draw it in different colors to help us?
Oh yeah. I don't. Whatever you need to do, it's fine. Let me scroll down and see what they got down here. All right, let's look at this question down here. It says, what product or products will be formed from the reaction of 1-bromo 2-methylpropane under each of the following conditions? So 1-bromo 2-methylpropane, so that's a 3-carbon chain with bromine on carbon 1 and CH3 group. Sorry. A CH3 group here. That's what that looks like. Let me draw that better. All right, so it's that. And if we subject it to these conditions that are shown in I, if my first step is to add magnesium and to do it in ether, that's what Et2O is, ether. Right, I want to show you something here. So here's 2, you add in formaldehyde.
Oh, the directions are telling us to react with this. Okay.
So then you add ammonium chloride and water. Right, so that's where your H plus is going to come from. All right, so this is what you call a sequence. It's a reaction sequence. All right, so the first step is to add magnesium to that alkyl halide. What am I going to get from that? What would that give me? And each step is subsequent to that.
A grenade?
It's going to give you a grenade. Good. So the first thing you're going to get is this. Right? And then that is going to react with the aldehyde in step 2. Are you following that?
The OH, I mean,
yeah. Right, yeah, right here.
Okay.
All right. I'm gonna write this out on a blank, in a blank space, because I don't want it to be all compressed. Here we go. So I have this. And then I had one was Mg and ether. H2 was formaldehyde. And then 3 was ammonium chloride in water. Right now, again, I said this is your source of H+. All right. So now, after the first step, I'm going to get a granule. I can't remember who said that, but you were absolutely 100% correct. Right? And then in the second step, if I react that granule with formaldehyde, which is here, what should I get from the second step? That's an aldehyde, right?
Oh, so it's gonna become an alcohol.
Well, no, not yet.
Oh, wait, then we got to intermediate. That group is gonna go where the MGBR goes.
So actually, let me just put this in. This is going to attack here, isn't it?
Mm-hmm.
And break the CO pi bond. So I'm going to end up with this, where that carbon now is bonded to the formaldehyde carbon, right? And then my MGBR is just here as a salt. All right. And then when I react that with the H+, what should I get?
With the it's gonna be an OH.
Right. I'm just going to convert that, where that O- is just going to become an OH.
Mm-hmm. With the magnesium bromide floating.
Mm-hmm.
Oh, wait, what did float with? Wait, did we do anything with 3 yet?
So with ammonium chloride, NH4, that's actually, let me show you what that looks like. Right, that's actually NH4 plus and then Cl minus, right? So the chlorine is going to end up here and then be plus NH3 because NH4 is where your H plus comes from.
Oh, what about the H2O?
Well, ammonium chloride by itself is a solid. So you have to dissolve it up, make it into a solution. That's why the water is there.
Oh.
Hi, good morning. This is Sonia Gonzalez calling in the morning director line. Can it be?
This is the wrong number.
All right. I'm going to stop here. We'll pick this up on Friday. We'll do some more examples. And I'm going to send you a video today dealing with retrosynthesis, how to work backwards. And then so we'll spend Friday and Monday walking through the problems in this worksheet or handout.
Thank you.
All right. I'll see y'all on Wednesday. On Friday. I'm tripping.
It's all right, Doctor.